Okay, this lesson is for Mrs. Cucci's College Now Pre-Calculus class. We are on lesson 7.5, which is vectors and applications. Alright, so vectors are a way to describe something, and they give a magnitude and a direction. Magnitude and direction. Unlike a scalar quantity, which is only magnitude, a vector quantity is going to give us a magnitude, which is magnitude is like speed, or the force that you put down could be a magnitude of 200 pounds, or a magnitude of, for speed, it might be 15 meters per second or something. But a vector is going to add into that the direction. It's not just that I'm going 15 miles an hour, it's that I'm going 15 miles an hour in a northeastern direction. So the way we draw a vector looks like a ray. It's got a straight line with an arrowhead. And we call, if this is, let's say, point A and point B, this would be vector AB. And we put a little sign over the vector like that. Okay. Now sometimes, instead of seeing it written like this, you'll see it written kind of in bold print. You'll see that mostly in textbooks. But don't, when you're handwriting it, you always draw this little sign above it for vector AB. And it always starts where AB. A is always going to be the point, and B is always going to be like this terminal side right here. Initial point and terminal point. Always goes to AB. Alright, so now we kind of know how to notate a vector. We can move on to finding out if two vectors are equal or not. So a vector is equal or equivalent to each other if they have the same magnitude and the same direction. So, for instance, if I draw this one, this vector, and this vector, these are equivalent. However, if I were to draw, let's say, this vector again and this vector, notice they are the same magnitude. When you're looking at a vector, the magnitude is going to be its length. So these are the same length, but they're going different directions, which means they're not equivalent. Obviously, knowing that, if we have one vector of a different magnitude than another, these are not equivalent either. So these are equivalent. These are not. These are not. And of course, we can put these two together. If I have two vectors of different magnitudes in different directions, they are obviously not equivalent. Okay, so let's look at a quick example here. Let's say we had a graph, and we have one vector here, and we're going to call this vector u. Now sometimes, I know I said earlier that a vector is labeled from its initial point to its terminal point, like this would be vector AB. We can also just call a vector u. So there's AB, vector, and you write it the same way with that little kind of half arrow above it. So this is vector u. And we'll say this goes from initial point 2, 4 to terminal point -1, 3. And we'll say we also have a vector over here somewhere. Whoa. Okay. So we also have a vector somewhere over here. Call it vector W. And it goes from initial point 4, -1 to terminal point 1, negative 2. And we want to know, are they equivalent? Are vector u and vector w equivalent? So the first thing we have to do is check their lengths. So we'll start with the length of vector u. Now the way we notate this is we put kind of like, they look like absolute value symbols. And that means the length of vector u. And we use the distance formula to find it, nothing new here. Change in y squared minus the change plus the change in x squared. So we're going to have change in y of vector u is 4 minus 3 squared, plus our change in x is 2 minus negative 1 squared, and we get our length of vector u is radical 10. Do the same thing with vector v. Distance formula. Vector v has negative 1 minus negative 2 squared plus 4 minus 1 squared, which is coincidentally radical 10. So this is only half of it. Now that we've checked the distances, we still have to check to see if they're in the same direction. And the way we can check to see if they're in the same direction, one of the ways is going to be to look at the slope. So, come down here. The slope of vector u is going to be 4 minus 3, y1 minus y2, all over 2 minus negative 1, the x's, and that's going to come out to 1/3. And if we do the slope for vector w, I think I call it w, yeah. Sorry guys, this is a w, not a v, one away. Just keep the notation straight. For vector w, we have negative 1 minus negative 2, all over 4 minus 1, which is also 1/3. So these are equivalent, because they have the same magnitude and the same direction. Okay, so besides equivalent, we can do regular mathematical operations with vectors, starting with addition. So let's say I had a vector that went like this, and we'll call that vector u. And then I have another vector over here that I call vector v. My sum, my vector addition, resultant is right here, and you should remember resultant from when we were doing the forces questions and law signs, law cosines, that area. We did trig with the vectors, and it's going to come back. But this right here, this resultant vector, is the sum of u plus v. Notice it goes from the initial point of my first vector to my terminal point of my last vector. That's kind of a quick way to do sums on graphs, if you can do it graphically. We're going to look at it algebraically, though. You may remember this from law of sines. We have the parallelogram rule. So if I have my vector u, and I have my vector v, and I have my resultant, I can, of course, say, okay, well, vector v is also right here. And there's my vector u. This is u plus v, my resultant. And of course, you can solve for these using your law signs, law cosines, whatever, given the information that you do have. So let's give these some values and try and solve it. Let's say we had two forces that act on an object, and we'll say the object is right here. And we'll say the one force is 25 newtons. So that'll be represented along vector u. And we'll say that the other force is 15 newtons if they act on it. Now we want to find the sum, or the resultant force, between the magnitude and the angle that it makes with the larger force. So this is the angle we're looking at right here. We need to find the sum, and we need to find the resultant. So the sum, the length of the sum, the magnitude of the sum, is going to be guys, one more thing I forgot to mention here. These forces are acting at a 90-degree angle to one another. That's going to be important in a second here. I know they don't look like a 90-degree angle, but they are. So if we have a right triangle, if this is a right triangle here, this is a right triangle here, we can use the Pythagorean theorem to find that resultant, the hypotenuse, and that's just going to be 15 squared plus 25 squared, and take the square root. And we're going to get approximately 29.2. So if you guys want, I can redraw. Come on. This really should look like this. Here's the 15, here's the 25. Here's the 15 again. Here's the other 25. There's my resultant. My u plus v that I'm looking for. Just to make it a little more clear. That's why I was able to use the Pythagorean theorem, because of this right angle. These two right angles. Okay. So I found my magnitude. Now I need to find my angle. Well, to find my angle, this angle right here, remember the angle the resultant makes with the larger force, I'll call it theta. Theta is going to equal the inverse tan of my sides, opposite over adjacent, just like a regular tan. So my opposite, here's my angle theta, my opposite is 15, my adjacent is 25, and so my theta equals 0.6. Okay. Sorry guys, my theta doesn't equal 0.6. 15 divided by 25 is 0.6. So I need the inverse tan of 0.6, and that's actually going to come up to approximately 31 degrees. The 0.6 is if you did that division. So I have a magnitude of 29.2 and a direction of 31 degrees. Degrees are generally considered a direction for vectors. Let's try one more vector addition problem here. Let's say I have two vectors, this time not at right angles. And I have this one. I don't know the length of this one. This one is going to be 190 units. And this length is going to be 48. Okay. The angle between these two is 60 degrees. We would like to know, now this of course means by the parallelogram rules that this is 190 and this is 48. And we would like to know the magnitude and direction of our vector v, I'm going to call it. That's our resultant vector, and we would like to know the magnitude of the resultant vector as well as this angle theta, the angle between the larger force and the resultant vector as our direction. So the first thing we need to do is find the magnitude of v. Now this time, since we don't have a right angle, we can't use the Pythagorean theorem. We have to fully do out the law of cosines. But this isn't hard. We have the length of v all squared. It's actually going to be outside of that. Just remember, the law of cosines is going to be some length that's squared. So here, instead of a squared or something, or c squared, write it as the length of v, and that's going to be quantity squared, equals, this vector is 48 squared plus 190 squared minus 2 times 48 times 190 cosine of 120. Sorry, I can't fit that quite in there. I'm getting the 120, of course. If this is a parallelogram, this angle is 60, that means that this angle is 60. These two angles have to each be 120 degrees. So that's where I'm getting that cosine of 120 from. So this means that my length of v is going to be the radical of this. And I can type that right in my calculator, and I'll get 218. So once again, that's 48 squared plus 90 squared minus 2 times 48 times 190 times the cosine of 120 degrees. Okay. That gives us this. Now, once again, I can use law of sines. I can't use just tangent here because I no longer have a right triangle. I need to use law of sines to find that out. So I have 48 all over the sine of theta, as well as what I just figured out, 218 all over the sine of 120 degrees. Do my cross multiplication, and I'm going to end up with sine theta equals 48 sine of 120 degrees all over 218. This means that sine theta equals 0.1907, approximately equal. And the inverse of that equals theta. And that's going to give us theta equals approximately 11 degrees. So this resultant vector has a magnitude of 218 with a direction of 11 with the angle with that large force. Alright, that's all we have time for today. I know this stuff is a little bit confusing, it's a little bit new, so make sure you bring your questions to class, and it should start becoming a little more clear once you start doing these on your own. Okay.